Section 38, volumes with cross sections. This is our first foray into 3D, and we're using normal 2D shapes as the base. So often you'll be finding the distance between two curves. So I'll do like a line in this. So that's our distance, this direction. And what we're doing is we're just putting shapes up into 3D based on this base distance. So like for semicircles, they pop up like this. If it was triangles, they'd be popping up into 3D like that. And it'd be a bigger triangle up here, like so. If that was straight up and down, which it's not, that's pretty weak. There we go. And so yeah, we're just building 3D shapes that have an area between curves and some sort of shape that pops up that we know the equation of. This table has a big list of all of the equations. We can have circular cross sections, semicircular, rectangular, square, equilateral, triangle, and isosceles right triangle. And the way the question's asked kind of tells you how you should go about doing each of these problems. So let's do the first example down here. So we have a shaded area between two curves, and we have a volume created with equilateral cross sections perpendicular to the x-axis. In these questions, when you say perpendicular to the x-axis, that means we're doing dx. It means the rectangles we're making, like up in our picture, this would be the little rectangle we're making, is dx wide, it's y tall, and it's popping up in some equation into 3D, like a triangle in this case, an equilateral triangle. So I'm going to grab the equation right away, root 3 over 4 side squared. We're integrating that thing. So our thing is going to look something like this. Now what we need to do is we also need to figure out like what our picture looks like. What are we integrating from and to? What's our variable we're integrating? Oh, we have dx, of course. I said that. So let's figure out what the picture looks like. So online this is included, but you might potentially have to draw this picture yourself to figure out where these meet. So at 1 here, y equals 1 is a flat line at 1. And then we have negative x minus 2 squared plus 5. Okay, that has a vertex at 2, 5. So 2 and 5. And I should see where this thing goes through 1 to see where the intersections happen. So I set 1 equal to negative x minus 2 squared plus 5. I subtract 5 over, I get negative 4 equals negative x minus 2 squared. I divide by negative 1. I get 4 equals x minus 2 squared. I get two equations here. For when we square root, we get two equations. One where it's plus, one where it's minus. X minus 2 equals 2, and x minus 2 equals negative 2. And then I just add 2 to both sides. And I get x is equal to 4, and x is equal to 0. Which means this thing actually passes through at 0 and over here at 4. Whoops. Cool, now that we know that, we know we're integrating from 0 to 4. Because this is our area that's between those two curves. So our next thing to do is to figure out what side is. So our side length in this is the height from here to here. So it's our graph, which is root x minus 2, x minus 2 squared, negative x minus 2 squared plus 5. That's the top equation minus the bottom equation, which is 1. So it's actually just 4 minus x minus 2 squared. And that's the way I'm going to bring it over to my integral. So now I'm going to come over here and plug that in for side in this integral. So I'm going to pull the root 3 over 4 out of my integral. Integral from 0 to 4 of 4 minus x minus 2 squared dx. And I need to square this because it's side squared. So I took the side, plugged it into this formula, squared that thing, boom, got my equation. Alright, we should do some expansion before we integrate this. X minus 2 squared. This inside is going to be, so I'm going to get root 3 over 4 times the integral from 0 to 4 of 4 minus x squared. The middle term would be negative 4x, but because we have a negative sign, it's going to be positive 4x. And negative 2 times negative 2 is positive 4, but the negative sign makes it a negative 4. And so these actually cancel out. And so really we're just integrating negative x squared plus 4x squared, because we still have the squared. I'm going to square this also before I integrate. So x squared squared, or negative x squared squared rather, is x to the 4th. My middle term in FOIL would be these two multiplied together times 2. That's a minus 8x cubed. And my last term is plus 16x squared. Alright, now that this whole thing is expanded out, I'm in really good shape to integrate this from 0 to 4 and multiply by root 3 over 4. Alright, my integral is x to the 5th over 5 minus 8x to the 4th over 4 plus 16x cubed over 3, integrating from 0 to 4 times root 3 over 4. And our last bit is to plug in 4 and 0. Thankfully in this case, 0 gives us 0, so I just need to plug in 4. So I'm going to do that where I have space over on the right here. So I get a root 3 over 4 in parentheses times 4 to the 5th over 5 minus 8 divided by 4 is just 2. 2 times 4 to the 4th plus 16 thirds times 4 cubed. And that's a solid place to stop. That is a good answer as it's written. Alright, that was a pretty heavy problem. Let's do another one. This time we're going to do different cross sections. This time I'm going to talk about a rectangle with height that is 3 times the base. My shape is going to be cut off by the curves x equals 0, x equals 2, y equals x, and y is equal to x squared minus 4. So I'm going to draw this out and figure out what picture I got in between this. So x equals 0 is just that vertical line. X equals 2 is this vertical line. Y equals x just goes up with a slope of 1. So this is 0, 2. And y equals x squared plus 4. This starts, or minus 4. This starts down at negative 4 here. And if I plugged in 2, I'd actually get up to 0. So this is a quadratic that kind of goes like that. But since we're cutting off at 0, this is my distance between the curves, is between these. So the same one's always on top. It's my distance between the curves, which is the base, because this is a rectangle, is just going to be x minus x squared minus 4. or just negative x squared plus x plus 4. All right, now that I have this, I can write my area equation. I am integrating from 0 to 2. My height is 3 times the base. I know what my base is. It's negative x squared plus x plus 4. And then I multiply by the height, which is 3 times negative x squared plus x plus 4 dx. That's it. I can pull the 3 out, no problem. And I just get 3 times the integral from 0 to 2 of negative x squared plus x plus 4 squared dx. If you're like, this looks like something I can integrate, yes, but not as it's currently written. We actually have to expand this out to be able to integrate this, because there's no chain rule part, so we can't actually apply the chain rule. So I have to actually square this term. I'm going to do the box method just for clarity's sake. Negative x squared plus x plus 4, negative x squared plus x plus 4. 16, x to the 4th, the easy ones in the corners. Okay, negative x squared times x is negative x cubed, and negative 4x squared here for negative x squared times 4. Negative x cubed, x squared, 4x, negative 4x squared, 4x. Cool. And I have all my terms. Okay, now I just dump them all in here. We're integrating from 0 to 2 of x to the 4th minus, remember when you do the box method here, your diagonal here is always, they're always going to have the same power, so you can just add them together. So I have negative 6x cubed. I have negative 7x squared. I have a positive 8x plus 16. Cool. Now I can integrate this, no problem at all. I get from 0 to 2 times 3 of x to the 5th over 5 minus 6x to the 4th over 4 minus 7x cubed over 3 plus 4x squared plus 16x. And now I just plug in 2. So it's 3 times 32 over 5 minus 16 times 6 is 96 over 4. Oh, that's clean. Minus 8 times 7 is 56. Plus 4 times 4 is 16. Plus 2 times 16 is 32. And that would be a fine way to leave your answer. And that's it for cross-section. So always find the area between the two curves, whether it's x or y. If it's perpendicular to the y, just rewrite your equations in terms of y and do the exact same thing. However, this one was way easier to do with x because all we had to do is distance between the curves. So writing our base was quite easy in this one. The hard part was expanding to integrate on this one. So yeah, just always set up, figure out your geometry formula, figure out what the base of your shape is, or what the radius of your shape is, or what the bottom of your equilateral triangle is, and then integrate your equation and plug in the points. That's it.